as usual, Francis is going to be speaking for about 40 minutes, and then we'll have a discussion afterwards. Please put your questions into the QA, but also Brett will be stopping during the talk to ask any kind of ad hoc questions. You can change today to keep it a little bit more dynamic than previously. So feel free to just raise your hand at the right moment and come in and ask your question.
All right, just checking because it was stuttering a little bit. Can you hear me out? Everyone can hear me okay?
Yeah, I hear you perfectly. You can see your slides too.
All right, great. All right, and just yell at me if any technical issues, just so I can correct them. But so thank you so much for the introduction, and thank you so much for the organizers for having me to talk today. And as was mentioned, I'm going to be talking about the importance of high quality data and building modern LLMs, lessons from DBRX. So I'm a part of the DataBricks Mosaic research team, and I wanted to start by giving you some context of what our mission is as a team within DataBricks. So our goal is to help everyone build and serve custom AI models using their own unique data to achieve the highest quality on their domains as efficiently and cost effectively as possible. And this ranges everywhere from customers who just want to use API calls to full pre-training runs. And so as part of this mission, we share our open source, or we open source our training code. And this includes some repositories you might be familiar with. This includes Composer, which is a training library built for scalability. Streaming, which is a library built around the challenges of working with large data sets. So how to stream data sets efficiently that are stored remotely in the cloud. LLM Foundry, which is our highly efficient and scalable training and fine-tuning code for popular LLMs. And Megablocks, which is our, yes.
It could be my internet connection. Could please anyone else? Forget what I just said. You carry on. It's my issue. Sorry about that.
Okay. Everyone else says it's okay?
Yeah.
Okay, great.
So GLT has raised his hand. So let me bring. Oh, he's taking it back down again. Sorry, someone raised their hand back down again. So you go ahead, Brett.
Okay. Yeah, your sound had been stuttering, and hopefully it's on your side, not mine. Okay. And so we use this training code to build, at the beginning of this year, we used this training stack to build DBRX. And so I want to start by just telling you at a high level, what is DBRX? So DBRX is an open LLM built entirely at Databricks. It's 132 billion parameters, but it behaves like a 36 billion parameter model. And it's a leading model on popular benchmarks. A little more detailed picture of what DBRX is sorry, just looking at the chat. DBRX is a transformer-based decoder-only large language model with a mixture of experts architecture. DBRX was pre-trained on publicly available online data sources. So no customer data was used to train DBRX. It was trained on 12 trillion tokens of carefully curated data and a maximum context length of 32K tokens. We estimate that this data is at least 30% better token for token than the data we used to pre-train the MPT family of models, which was the first set of open models we released in 2023. And we used domain at the end, we used domain upsampling for pre-training, where we changed the data mix at the end of train in ways that we found to substantially improve model quality. And the compute used to train this model was 3,072 NVIDIA H100s, and including pre-training, post-training, evaluation, red teaming, and refining, this took place over the course of about 3 months. And then at launch, DBRX performed many open models on language understanding, programming, and math. Sort of humorously, this lasted for about 1 week. But as a company that adapts models to new domains and like really builds on top of the open ecosystem of large language models, we're really excited about this pace of improvement in open models. So the question is, why did we build DBRX? And as hinted at by this previous slide, it wasn't we were trying to build the world's best model. What we were doing was we were upgrading our LLM training stack, and we were stress testing and improving DataBricks for Gen AI. And in this talk, I'm going to be talking about the part that I played in this model, which was I was working on the data team, and I'm going to be telling you about the tools we developed for DBRX to help you understand and leverage your data. So let's start by just quantifying what we saw as the value of better data in training our models. I'm going to be talking about this gauntlet score throughout. We're going to more carefully define it in the first section of the talk. But just so you know, it's an aggregation of about 37 popular NLP metrics, and the score is out of 100%. So it's sort of an aggregation of metrics measuring the quality of a model that we've developed. The model we trained in April 2023, MPG-7B, we trained it for 1 trillion tokens, and its gauntlet score was 30.9%. We, as part of preparing for DBRX, trained the exact same model for the same number of tokens, but we changed the data mix. And looking at our new data mix, we were able to get an 8.1 percentage point improvement in this gauntlet score just by improving the data. We also repeated the experiment where we trained the model for half as long, and with a better data mix, we were able to still get a better model with half as much data. I see a hand raised. Is there? I see Q&A. Okay. I'll stop at the end of the section and take questions if we have it. Okay. So the question is, how did we do this? How did we improve our data mix? And so there are many key questions about data that you want to ask when working with pre-training data sets. The first is, how should you mix your data? This comes down to a question of new tokens versus repeating tokens. How much can you repeat tokens without seeing degradation? There's the perennial question of what even is good data, so quality versus quantity in your data, and what pre-processing steps should you do with your data? Should you deduplicate your data? And the answer we always have as a team at Mosaic Research is we have to run experiments. The problem is models don't really learn like we do, and so we have to let science rather than intuition be our guide. But we immediately run into a challenge when we start to say, okay, we're going to do experiments to study our pre-training data mix. And that is pre-training models to learn about your data is expensive. These experiments cost a lot. And there's a simple reason for this, which is that on challenging benchmarks, you need to look at models at scale to get above the noise floor. So a classical example of this is NNLU, which is like a 4-choice multiple choice question. If you look at the accuracy and it's around 25%, that means the model is essentially just guessing. And so the first thing you should do anytime there's an NNLU score report in a paper is check if it's around 25% to see if the model's gained signal on NNLU. And a good estimate you could keep in your head for like what a lot of these metrics like NNLU, GSM-AK, and human eval, what sort of threshold they require to start to see signal is a 7B model trained for 1 to 2 trillion tokens, essentially the scale of the Llama 2 models. So there's a few ways you can deal with this problem. One of them is to make fewer bets, but make them bigger. And our big bet when we were looking at DBRX was increasing the amount of code data that we included in our model. So what we did was we would fix the amount of sort of the mix of other data sets, and then do some sweeps where we increase the amount of code data and saw what sort of the trade-off was in our coding and reasoning performance versus for getting on other benchmarks. And we were kind of surprised about how much code we could include in our data mix before we started seeing degradation on other benchmarks. But that's not going to be the focus of our talk today. What we're actually going to be focusing is the tools that we developed to run pre-training data experiments for faster and cheaper. And so the roadmap that we're going to go through today is sort of how we would walk through customers who want to characterize their own data sets and what are the steps we would take with them to sort of understand their data and to build a data mix that would hopefully be successful for pre-training. So the first thing is you always have to start with evaluation. You have to start by defining and understanding success. And so for that, I'm going to use the example of our Mosaic evaluation gauntlet and how we thought about characterizing the evaluations in that set of evals. And then we're going to talk about two tools for studying your data. Continued pre-training, which is putting more data into your model at the end of training, and domain upsampling, which is emphasizing high quality data in the final stages of training. And I'll just briefly mention that what we're not going to cover is the DBRX architecture. MOEs and the peculiarities and how to train them efficiently. Our pre-training and engineering team did a really incredible job of working through those issues. There's also the question of inference efficiency and data tooling, which, given that we're DataBricks, you probably won't be surprised to learn is Spark. And I also wanted to acknowledge amazing collaborators on this work: Mansij, Cody, Sean, Tessa, and Jeremy. And DBRX is really a joint effort of the DataBricks Mosaic research team. Okay. Was there a quick question before I jumped into the first section?
There is a question, Brett. For some reason, Zoom is not allowing me to unmute Giotti. So I'm just going to. I just don't think it's going to allow me to unmute anyone. There's something going on with the Zoom interface. Sorry about that, everybody. So I'm going to read out questions instead. So the question from Giotti is, what was the TGE score for?
The TGE.
Yeah, I don't know if that's a misspelling or if that's what the intention was. TGE is what we have in the QA. Giotti, please clarify if there's anything I've missed. The gauntlet score.
Oh yes, I'm going to define that right now. So that's the next section.
Okay, right.
Yes, so the gauntlet, actually perfect segue. We're going to start with evaluation, which is, you always have to remember you can't make progress until you know what success looks like. And that's sort of the key of developing evaluation metrics. It's always the first thing we tell customers is, we can't really help you with your model until we have some way of measuring whether or not it does what we want. And so to sort of talk about the way that we think about evals, I'm going to use the example of our Mosaic evaluation gauntlet. So this is our set of benchmarks for evaluating the quality of models, and it's composed of 39 publicly available benchmarks split across 6 core competencies. And the gauntlet was sort of developed when we were training the MPT family of models back in 2023, when we were sort of overwhelmed by the number of evals you would try and run and sort of compare across models. And so we had this idea that what we wanted to do was group these evals together into sort of capabilities so that we could get some better like summary statistics across like what different capabilities a model would be good at. And so let's quickly go through the capabilities that we came up with for the Mosaic evaluation gauntlet. So the first is world knowledge. This measures the model's factual knowledge. So evals like NMLU. Common sense reasoning evaluates the model's ability to do basic reasoning, requiring common sense knowledge. Language understanding is just sort of the basics of understanding structures and properties of language. Symbolic problem solving is testing a diverse range of symbolic tasks, including like arithmetic and logical reasoning. So GSMAK, which basically tests mathematical ability, falls in this category. Reading comprehension, which is testing a diverse range of symbolic tasks, including, again, arithmetic and logical reasoning. And so again, there's a little, there will always be overlap in looking at model capabilities. And then lastly, programming, which is its ability to generate code, which is currently just human eval, but hopefully will be expanded a little more. So when we work with the gauntlet, what happens is in all the benchmarks in each of these categories will first be averaged within that category, subtracting out the noise floor. And then when we report a core average, this is the average of the 6 categories. So if you want to dive more into the gauntlet, we've got a great blog post that will sort of go through all the different evals. Now, what I'm going to talk about today is the experiments that we did to calibrate the gauntlet, which is our term for we wanted to understand whether these evals were actually helping us distinguish between model quality before we started down the path of choosing our data mix for DBRX. So again, like, what is quality data? Another perennial question is, how to identify useful evals? And so we tried to start with a very simple prior, which is that useful evals will distinguish between model quality. And the method that we were going to use is we trained a series of 2.4 billion parameter models on the same data mix, but for a range of durations. So from 20 tokens to parameters to 500 tokens to parameters. Essentially, we just kept putting more data in the model and assumed that, sort of scaling holds, and this will give us better and better models. And then we looked at how the different evals performed across this sequence of increasingly advanced models. Again, this is all assuming that the model is improving at the capability that we're trying to measure with additional training. So this is the type of sort of plot that you would get out from this experiment. So our challenge is an eval that's a 4-way multiple choice question about different basic science questions. And each of these curves are using different number of shots. So how many examples of the task do we give the model in the prompt before we actually have it do the task? And so the dashed line here will be whatever the noise floor is for the eval. And then each of these curves shows how, for the different number of shots, how does the eval scale as we increase the amount of training and supposedly the model quality. So this plot right here shows what we want to see, which is like, as we get more and more advanced models, the eval scales, it continues to go up as the model gets more and more training. And also another very nice quality of this eval is that this is true across the different number of shots. There isn't different behavior across shots. So we performed this experiment for all the different evals that are in the gauntlet, and we sort of categorized the evals into several different categories. So the first is what evals just like the ones I just showed you, which is well-behaved scaling, and it's robust to few shot settings. So there aren't, no matter what number of shots I use in this sort of set of shots that we were experimenting with, I get this scaling where the eval performance increases with increased training of the model. And so this is great. This is what we want to see, and these are very simple. We also got a second group, which is well-behaved scaling, but only for a specific few shot setting. So what this allowed us to do is sort of, we're going to choose a number of shots that we're going to use for the eval. And so if we see that this scales poorly for 0 shot or 1 shot or something like that, then we can, in our gauntlet, make a specific number or a specific choice for the number of shots we're going to use in that eval to sort of get the behavior that we want. Then group 3 is the metrics that behaved like how we didn't want them to, which is poorly behaved scaling, which is something like I put more data into my model and my eval eventually goes down. These might warrant more specific investigations, but some of these evals were evals that we eventually removed from the gauntlet because we thought they were just creating more noise. And then lastly are sort of the evals that are challenging, where we're just sort of at the noise floor. So MMLU, again, is a classic example of this. The models we're training weren't competent or weren't at a high enough flop scale to see signal in MMLU. So the aggregate of this experiment was these guided our developing the gauntlet v0.3, which served as our guide for choosing the DBRX data mix. And really the emphasis here was we looked at the evals and we looked at how they scaled, and people also went and read the actual evals. And so this was an effort to basically understand if our metric for success was measuring sort of what we expected it to. And evals are sort of the thing where there's always lots of directions for improvement. For example, adding more programming evals, repeating this experiment with other models and data mixes. And then for many customers, what we want to do is we want to augment the gauntlet with domain-specific evals. And in all these cases, looking at the evals is always essential to make sure it assesses sort of the desired capability you want for your model. So that was our process for sort of developing the gauntlet v0.3. And we're going to sort of use that now as our guide for thinking about different pre-training data. So I can pause here if there are some immediate questions before the next section.
I had a question actually.
Yeah.
So you said that when we spoke about this idea that you're going to train these smaller, like 2.4 billion parameter models, and you said, assuming scaling holds, then you can apply your learnings from this experiment to like a scale up. I assume you mean like a larger model. So you said assuming scaling holds. Does it hold?
So when I said that there, I was more talking about the implicit assumption that like if I put more data in, I'm getting a better model, right? So I'm not using this to extrapolate to larger models in this case. It so like when I look at these curves, right, you know, the underlying assumption that says this sort of shape of curve is good for the evals is assuming that I actually have a sequence of better models on whatever I'm trying to measure. And I just wanted to emphasize that, that is sort of an assumption that we had to put into this experiment. Now, when you talk about going to bigger scales, right, like that's where these noise level benchmarks come in. So like if we wanted to sort of, do the same experiments for these more challenging benchmarks where we wanted to see like, okay, once we get above the noise floor, do they scale in the way we expect? The experiment there would require, larger models, right? And, something like MMLU is, and I don't know if GSMAK is on here, but, or human eval, you'll see in like all the larger models, those do have very like reasonable scaling with model quality.
Okay, so if I understand correctly, you haven't done any work on whether these, for instance, can you extrapolate from the optimal data mix on a smaller model and extrapolate to a larger model? That's not what this is about.
So that's what we're going to talk about next, right?
Okay.
So like um when I said, pre-training data experiments are expensive, the key thing is, that what you're saying there with like say we train a 2.4 billion parameter model and it's just getting noise at MMLU. I would argue that typically you can't extrapolate. You cannot extrapolate, which data mixes are working. You can sort of throw different data mixes at it and you'll just get noise at every time and it won't tell you anything about your data. And so the next two parts of the talk are sort of the strategies that we develop to sort of get around this, which is to sort of work with models that are towards the end of training and do our data interventions there.
Okay, thanks. Any other questions from the audience? Okay.
Great. Okay, so let's move on to these data interventions. So the first thing we're going to talk about is continued pre-training. And so continued pre-training is a very simple idea. We're just going to take a pre-trained open model that you have access to. You could take Llama 2, Llama 3, any open model that you have. And we're going to take more data and continue to train the model and see if that improves the model on different evals. So here what we're doing is we're going to do a particular learning rate schedule, which is like, so this model has been annealed, i.e. the learning rate has been decayed at the end of training. And so what we have to first do is we have to sort of warm the model back up. So we increase the learning rate, then we train at some constant learning rate for a while, and then linearly decay it. And then you might ask, what is the difference between this and fine tuning? So there's two sort of key differences. This is more tokens than fine tuning. So typically, like a lot of our experiments are putting in something like 15 billion to 80 billion additional tokens. Normally, the number of additional tokens you're putting in for fine tuning is more in the millions. And also, we're still doing next token prediction. So you can basically think of this as just doing more pre-training, but we're doing it to a model that has been cooled down, and then we're going to sort of warm it back up and train it on some additional data. So for showing you how continued pre-training works, we're going to work with two example data sets. So Open Web Math is an open data set of 14.7 billion tokens of mathematical web pages filtered from CommonCrawl. And FLAN is a collection of tasks and methods for instruction fine-tuning converted to a pre-training data set by concatenating the prompt and responses. So what you can imagine is like, say we had never encountered these data sets before, and these were two data sets that a customer had. I'm going to show you sort of the set of experiments that we can do to go through and understand what tasks these data sets might help and hurt. So the first thing we're going to do is we're going to take Llama 2.7b as our starting point. So we were doing these experiments, I think, back in February, way before Llama 3 came out. And we're going to do one epoch of continued pre-training. So that's what CPT stands for on Open Web Math. So that's continued pre-train for 15 billion tokens. So on the left, you can think of this as my metric for learning. So I want to see if Open Web Math helps me with MMLU. You could choose any metric that you were interested in. Open Web Math will also really help with GSM-8K, which is a math data set. But at the same time, I want to monitor how much I'm forgetting on other tasks. And that's what I'm going to use core average for. So core average, again, is my aggregation of all the metrics. In this section, I actually won't be including the programming category just because we're going to just look at the other metrics in this case. But again, you just need a metric to measure learning and forgetting. So what this plot shows you is what happens to these metrics as I sweep the learning rate for the different settings of this continued pre-training. So for example, here, this is 1e to the -5. I'm first going to warm up the model to 1e to the -5, train at a constant 1e to the -5 for a while, and then linearly decay at the end. And I'm going to repeat that for a bunch of different learning rates. So the first thing you'll notice is there's actually a big difference in this performance based on the learning rate. And we always tell customers it's really key to sweep the learning rates before you make conclusions, right? This is what, this is the success of continued pre-training is sort of highly dependent on you making sure that you explore the different learning rates. But the other remarkable thing you can see here is if you look at the 1e to the -5 learning rate, and actually all these ones except for this high learning rate over here, we're actually learning and improving on MMLU without any cost to our core average, right? So we're improving the model on a specific benchmark without losing other capabilities. So in this experiment, I've swept the learning rate. Now let's take our best learning rate, which is 1e to the -5, and instead sweep the duration. So I'm saying, okay, if I continue to put in different amounts of, tokens of Open Web Math, and in each of these, right, I'm going to cool down at a different time and look at the performance of the model. I see that I can, at some point there's going to be a good trade-off where I can get the most performance in MMLU without losing too much in my, forgetting in my core average, my basket of other benchmarks. And what we see here is we're able to get a 6 percentage point improvement in MMLU without any degradation on Gauntlet core average, without any forgetting, which is very exciting, right? Like it's exciting that you can put a small number of tokens in and get such a huge improvement on a benchmark like MMLU. The other thing that the Gauntlet allows us to do, right, is like, okay, so let me just go back to the slide, right? So on the right, I have core average. I want to now say, all right, what if I break down core average by the different capabilities that the Gauntlet measures, right? And now if you look across this plot, you can very quickly see, right, some of these categories are being helped by Open Web Math, and some of them are being hurt. So like symbolic problem solving, we're getting a performance boost, especially in GSM-8K, which is a math eval. And then the two metrics that are sort of categories that are sort of being hurt by this are world knowledge and language understanding. So if we want to, we could dig further into those and see, which of the evals are being hurt by putting in Open Web Math. And then like common sense reasoning is sort of flat. So because we have this framework from the Gauntlet, we can sort of like do this barcoding essentially of the data set where we can see, all right, which metrics does this help and which metrics does this hurt? So now let's try and take this a step further. We tried this with Open Web Math. What if we have another data set that we want to characterize and then try mixing them together? So again, on the left, I have MMLU accuracy, and on the right, I have core average accuracy. And I've put 2 reference points on this plot. So the red line is the Llama 2 7B performance, and the dotted black line is the Llama 2 13B performance, a model that has been trained for a lot more flops. And again, so the left is our learning metric and the right is our forgetting metric. So I've put on here the result that we get from Open Web Math. Now what happens if we try and do continued pre-training on Flan? Now, each of these curves are the best result from a learning rate sweep. So we did that learning rate sweep initially, and then we saw what we could get. So if we just do continued pre-training on Flan, not great, right? We get more forgetting than we would with Open Web Math. But now we can start to try different mixes of this data set. So for example, what if we do 2/3 Open Web Math and 1/3 Flan? Now we're actually getting better performance than either of these data sets individually. And finally, the best mix that we found was 85% Open Web Math and 15% Flan. So we're learning a little in these relatively small experiments, especially compared to pre-training, we're learning about these different data mixes, the evals they affect, and sort of what are the effective ways that we can combine them. But we have sort of one last trick up our sleeve to improve this even further, and that's by weight averaging to prevent forgetting with the original model. So this is very simple linear weight averaging, where you're going to do an average between the weights of your original base model and the weights that you got from your continued pre-training. And so, you choose some value of alpha between 0 and 1, and that controls how much of the base model you mix in and how much of the continued pre-trained model you mix in. And, it's also sort of affectionately referred to as model soups. So now in this plot, I'm showing on the x-axis my core average accuracy, so my forgetting metric. And on the y-axis, I'm showing my MMLU accuracy. And we start down with the base model at the bottom left corner. And so far, we've been able to get this best continued pre-training model towards the upper right-hand corner. And now what happens when we soup? So these lines that I'm showing connecting these two are the different weights of merging these two models, right? So I start here and I combine, 80.8 times the weights of my base model plus 0.2 the weights of my continued pre-training model. And I look at all the different combinations of this. And incredibly, what we can do is we can get a point that's better than either the base model or the CPT model over here. So we're basically able to get into this territory where by putting in 40 billion tokens, we're able to rival the performance of Llama 2 13B, which is a model trained for way more flops. So let's just put this back on our original plot that we have here, right? So now this red square is the result of doing souping of the best CPT model we had with the base model. And just to drive this home, I always like to put this on a scaling plot, right? So these scaling plots are log plots where the x-axis is the number of training flops, and then the y-axis is the error. So either one minus the accuracy for MMLU and 1 minus the accuracy for core average. And so the blue line is the original scaling that you would get across the set of Llama 2 models, right? So we have Llama 2 7B, 13B, and 70B, and we can draw sort of a linear line on this log plot to see how these models scale with MMLU and core average. And then this arrow shows, by putting in 40 billion additional tokens, which is not very much compared to how many more you had to do to train Llama 2 13B, you're able to push this all the way up to the same performance as Llama 2 13B through this combination of understanding your data, mixing the data together, and then also doing this souping. Okay, so this was a bunch of experiments on Llama 2 7B. The last sort of question we wanted to ask was, does it scale, right? As you put more and more data into a model, is this intervention going to be less effective? So let's look at what happens when we do this same intervention, but for Llama 2 13B. So here I'm showing the same similar idea of plots, but I'm showing you both of the learning rates we tried for Llama 2 13B. And so in the best case, we get a 3.3 percentage point improvement on MMLU without degradation on core average. So this is looking at how far we were able to get above the baseline in MMLU. And then we did the same thing for Llama 2 70B. And here we're able to get a 1.8 percentage point improvement on MMLU without degradation on Gauntlet core average. So we're still getting improvements. So let's now plot this on a scaling plot to sort of see the idea of are we sort of getting diminishing returns, right? So this is MMLU error. I've drawn sort of the linear regression here of the Llama 2 models. And then I've done the linear regression across here of the performance that we got from our CPT models, just trained on OpenWebMap. This isn't all the fancy tricks. This is just doing continued pre-training on OpenWebMap. And so what you can see is the scaling of the CPT models is slightly worse than the original Llama 2 models in the sense that they're not parallel lines. They're sort of starting, to come towards each other so that they'll probably cross at some point. But we're still seeing gains near 10 to the 24 flops where Llama 2 70B is trained. So first of all, continued pre-train has given us a better model for a pretty small investment of flops. And with customers, they may have some data set that they want to add into their model to improve the capabilities. And so continued pre-train allows them to quickly do that. And then we can use this weight averaging to mitigate forgetting. But it also enabled us to study these two data sets without doing full pre-training runs. We learned a lot about OpenWebMap and Flan from doing these experiments. Okay, let's take questions on that section. I saw a few questions pop up.
Yeah, sorry everyone for the issue with the muting, but I'm just going to read the questions out again. So we've got a question from Sandy. What optimizer do you use when you're sweeping the learning rate?
Yeah, so we've been using Lion, but you could do this just as well with Atom. With the learning rate sweeps, right, the important thing is that you do the sweep more so than the optimizer, but you'll probably end up with like different learning rates if you use Atom versus Lion.
Okay, and then Dev is asking, Dev is asking for some clarification. Are these the steps? Learning rate sweep followed by token sweep of multiple data sets, tokens in different ratios. Do you iterate with different learning rates?
So typically what we do first is like we do an experiment like this to sort of zoom in on what is the range of useful learning rates. So basically we don't want to do the duration sweep for learning rates that are going to be, probably not useful. So in this case, if you did, you did this first experiment here for Llama 270, what you'd probably do is take this learning, I don't know if you can see my mouse, but this would be 3e to the -6 and 1e to the -5. We would probably take the two best learning rates and then do the duration sweep. But the only reason not to do the full duration sweep for all of them is just, why waste compute when you first get, a little bit of an idea of which learning rates work, and then you choose maybe one or two to do the duration sweep. So that's for a single data set. It becomes a little more complicated in the mixing. So like for individual data sets, right, you sweep the learning rate at like one epoch and then sweep the duration for the two best ones. For the mixes, you're going to have to repeat that probably for like all the different mixes you want to try. So there's a little bit of intuition there, right, of like, okay, maybe try a mix and see, which directions are helping. But to summarize, once you've chosen a data set or a mix, first you sweep the learning rate for the first epoch, and then you choose the best one or two to do a sweep of the duration.
Okay, and thank you for that. And then we have Piers asking a question. What sort of time or cost are you talking about with the continued pre-training experiments?
Yeah, so for the 7B model, so first of all, like the cost is going to be completely determined by like the size of the model and the amount of tokens you want to put in. Generally, you could do really small CPT runs on like, all right, I'll just say like what we typically do for these. I think normally we do like 40 H100s for like a continued pre-train run, and then they're done pretty quickly, right? So I think with like a set of 40 H100s, some of these duration sweeps you could probably do in, I think, a few hours. It's been a little while since I, probably like 5 to 8 hours. You could do it on a smaller number of GPUs and do it faster. But yeah, they're still expensive, right? You need a lot of H100s, but certainly not in the territory. I mean, like you can estimate that to do a full like training run for a llama to like a 2 trillion tokens, right? Probably going to be on the order of a few $100,000. Unfortunately, they're really expensive runs. CPG is much cheaper was the point I was trying to make.
Got it. Okay. Oh, okay. So someone's just asking, will this talk be posted online? It will indeed. It will also be on our YouTube channel. So you can subscribe to our YouTube channel to get the notifications. It's London Machine Learning. You can just Google London Machine Learning Meetup YouTube. Thanks for that.
All right. Any other questions?
No.
All right. Let's go to the final part of this talk, which is domain upsampling. And this is all about getting more out of your data during pre-training. So continued pre-training was assuming that, you had some model that had been cooled down and we're just going to warm it up and do, maybe 15 to 30 billion additional tokens of continued pre-training. Domain upsampling is moving this further, and when you're doing a full pre-training run, and it's a simple intervention where we increase the percentage of domain-specific data towards the end of training. This is the last 10 to 30%. To start with, we found this is very useful for improving model performance on benchmarks, for getting more out of your high-quality data. But as I've tried to emphasize at this talk, I think even more exciting is it's a tool for understanding which of your data sets matter for improving evals that's also cheaper than full fine-tuning. So let's start with the rough outline of the original data mix that we used for this experiment. So these were the data set categories that we were thinking about. So large-scale CommonCrawl, just the general CommonCrawl scrape type thing. Small-scale CommonCrawl, which has been like filtered in some way. Domain-specific data, which is much smaller data sets, which are for a specific domain, and code data. So what I'm showing you here is sort of the proportions that we used across these broad categories to start with for our data mix. And again, like I said at the beginning, one of our big bets is really increasing the amount of code here. And so we're starting already with 21 or almost 22% code in our data mix. And so I want to start with showing you a baseline, which is for how this original data mix scales. And this is going to be across 4 different challenging evals that we've been talking about here. So MMLU is sort of language understanding and world knowledge. GSM8K is mathematical reasoning. Human eval is coding ability. And then Mosaic Gauntlet is our sort of aggregate of all these evals. Okay, so let's first look at this plot, which is very similar to the ones that I was showing you in the slide before, which is this is a log plot of the scaling of llama. So on the x-axis is the log flops. On the y-axis is the error on the benchmark. And then I've done linear regression in each of these cases to show you the scaling curve for the llama 2 series of models. And then the 2 squares are showing you how our data mix scales for if I train for 500 billion tokens and if I train for 1 trillion tokens. These were the 2 models I was talking about at the beginning, that we were, training on this data mix and, seeing really great efficiency improvements over NPT. So you can see that our 2 models with the square, the models lie at or below the llama 2 scaling line. So like MMLU is right on the scaling line. Others of these are below. For example, for human eval, this is because we use significantly more code in our mix than the llama 2 mix. But to start with, the important takeaway from this is that our data mix is performing at or better than the llama 2 scaling. So now what we're going to do is we're going to take these training runs, but we're going to repeat the final 20% of training, and we're going to upsample our domain-specific data. So we're going to get completely rid of large-scale CommonCrawl, and we're going to do 30% small-scale CommonCrawl, 35% domain-specific, and 35% code. So showing you these plots again with just the 1 trillion tokens on them. This is what happens when we do domain upsampling. So it's moving straight down in this scaling plot, right? Because there's no additional tokens. We just sort of changed the data mix during the last part of training. And this simple intervention had a huge impact on model quality. So, you can see from each of these sort of, blue arrows on here on these log plots, this is the change we got from doing this domain upsampling intervention. And I want to emphasize this is a simple intervention. We sort of shifted our data mix to emphasize domain-specific data sets. Now, the next question you might ask is, okay, can I get better performance if I just, do domain upsampling the whole time? Should I just push this back to the beginning? And so we did this sweep where we changed the duration of how long we did the domain upsampling from 0, which is like the original training run, to 30% of training, which is the last 300 billion tokens. And so you can see here some metrics stop improving with increased domain upsampling. We found that around 20% was sort of like our best trade-off point, but we have work in progress where we've sort of successfully mitigated this with multi-phase changes to our data mix. So instead of just doing your domain upsampling, doing sort of a more gradual upsampling of the data over the course of training. And like I said, this is great. We're getting boosts on our metrics, but it's also a tool for understanding your data sets, for understanding which evals a data set helps, hurts, or has no impact. So what I'm showing you here is an experiment where we did several different variations of the data mix during the final phase of training to characterize a certain subset of our data. So we had some domain-specific data that was focused on math, and we took out those data sets during the domain upsampling period. And we saw that this significantly hurt several of the metrics where we were seeing improvements. So it significantly hurt MMLU, it hurt GSM8K, and it hurt core average. And the only thing it didn't hurt was human eval, right? We sort of kept the code the same, and we had removed these subsets of data that were math focused. And so by just doing sort of these perturbations to our data mix during this final phase of training, we're able to see, again, which evals are being impacted by this data and what we might be able to target by increasing that amount of data in the data mix, and what might be the cost of, the other evals that we might hurt. So I just wanted to also share sort of two success stories of other people using domain upsampling. So we we have our friends at AI2, which we're training Olmo, which is this great, very open large language models with open checkpoints and data, et cetera. And this plot is showing a very similar scaling plot. They've got MMLU going up, flops versus MMLU accuracy versus MMLU error. But they saw a 24 percentage point improvement on MMLU from improving their data mix and adding domain upsampling. So again, huge gains from just thinking about your data and sort of using these data intervention techniques. And recently, we're also really excited to see that, in the Llama 3 paper, they mentioned that they used a very similar technique for working with their data sets to judge the value of their small domain-specific data sets. So this is sort of the TLDR of my talk for today. So the key is, we try to emphasize to people that models don't learn like you. So experimenting with your data is really important, right? You need to actually, you need to actually do experiments rather than just sort of trying to intuit out what the data is doing. But we have this problem that getting signal on your data requires training at large scales. And so what we've been working on is ways that make experimenting with your data faster and cheaper. Still kind of expensive to work with large language models, unfortunately, but these are better methods, or these are much more practical methods than doing a bunch of different pre-training runs with a bunch of different mixes. And in both cases, the key is sort of doing data perturbations at the end of training. So with continued pre-train, we're putting more data into our model at the end of training. And with domain upsampling, we're emphasizing high quality data in these final stages of training. So both methods enable you to better understand how your data affects the capabilities of your model. And also we've shown that it also helps, you're able to boost performance on your model, getting efficiency gains out of having a better data mix. I just wanted to emphasize some places where you can find out more about this work. So our team has a research blog. So for example, this Calibrating the Gauntlet has a blog post where you can dig more into it. And hopefully more and more of this work will be out in blog posts and papers. We actually have a paper that's going to appear at Column on this domain upsampling work. So the paper is called Does Your Data Spark Joy? Performance Gains from Domain Upsampling at the End of Training. And then I also wanted to emphasize a paper by my colleagues called Laura Learns Less and Forgets Less. This paper also has some continued pre-train experiments related to programming and also some more stuff with open web math. The purpose of that paper is to compare sort of these full fine-tuning or continued pre-training to Laura. But if you're interested in sort of the results of doing continued pre-training with code, this is a great place to find some results there. So that's the end of my talk, and happy to take any more questions.
So we got the questions coming in. Audience members, please add a few more questions if you can. I'm just going to sneak one in right at the beginning. Brad, for talking about domain upsampling, are you doing any annealing of the learning rate when you do that at the end of training?
So we're using the same learning rate schedule that we were already using. In these particular experiments, it was sort of an inverse. So the same idea where you do a linear warm up and then you either do constant or sort of like a slight decay and then a decay at the end. Sorry, so inverse square root learning rate, if you're familiar with it. That means that the cooldown is happening during the final 20% of training, which is the last 200 billion tokens. So most of our domain upsampling is happening during this annealing period. We're currently exploring how this interacts with other learning rates. So say if you're doing cosine decay, right, there's a longer decay period. Some interesting questions about how that interacts. Is it more or less effective during this annealing period? But the kind of maybe a short answer to your question here is that the last 20% is the annealing period for the learning rate for these particular experiments.
Right. And then just maybe you covered this and I missed it, but what is the can you quantify the impacts of doing domain upsampling during the final phase of training compared to just upsampling for the bulk, having a static data mix and upsampling, changing the data mix effectively?
You mean domain upsampling versus the original data mix?
I mean, no. I mean, instead of domain upsampling during the final phase of training, comparing that to domain upsampling with a static data mix.
Domain upsampling. Okay, sorry. Can you just define domain upsampling with a static data mix?
I mean, don't change the mix during the course of the
training. Yeah. Sorry. That's what this plot is supposed to show, right? This is the squares are not changing the data mix, and the diamonds are changing the data mix during the last 20% of training.
But are the squares here? So you're not changing the data mix, but is the data mix the same as the final data mix of the diamond?
Oh no. Okay. So you're saying what if I did the domain upsampling mix the entire time?
Yeah, exactly.
Yep. Okay. So that's where, we didn't do the experiment where we did the final domain upsampling mix the entire time, but we did try and pull it back as far as we could. And presumably what will happen is these trends will continue sort of where you would get a worse score on like MMLU and core average. But we have not done the exact experiment that you said, which is like train with the domain upsample data mix, basically based on these experiments, which was we started to pull back when we did the domain upsampling, and we're starting to see degradation in performance.
Cool, thank you. Okay, great. So we've got plenty of questions coming in. So, Drew, have you seen continued pre-training perform well for completely out of domain data like genomics or DNA sequencing?
Yeah, that's an excellent question, and it's sort of our research agenda right now, right? Is like, a lot of times a customer will have, their set of internal data that is something that wouldn't appear in general web scrapes. And we're sort of exploring now, like how effective continued pre-train is on those data sets. So I would say this is a thing to stay tuned for. I will say one of the things for Llama 2 that I think like Open Web Math was especially, I think continued pre-training tends to be at its best when like you're doing continued pre-training with something that is not emphasized in the original training mix. And I think, in the Llama 2 case, right, like the scores were generally lower from GSM-8K than other models. And so I think, in that case, Open Web Math could have been a really effective thing to sort of cover maybe something that was delinquent in the original pre-trained data set. But stay tuned for more work on like continued pre-training with domain adaptation.
Cool. So we've got a question from Piers. With continued pre-training, what would be the minimum amount of additional data needed to make it worthwhile to make a difference? Would it be worth doing it with only, let's say, 100 million domain-specific tokens?
Again, this is a question that can depend on the model and the data set and when it was originally trained with. I can give you some context in that if you look in the LoRa learning and forgetting paper that I mentioned at the end, there we did some experiments with like under 1 billion tokens of Open Web Math. And we did see some improvement, but like you really start to see more improvement, I think around the 2 to 5 billion scale of tokens. So I would say that like it's definitely worth trying if you have a small amount of data, but I think where you really start to see lots of benefits from continued pre-train is probably, at like, about 500 million tokens or something like that. But again, with all these things, you sort of have to try the experiment, unfortunately, because every model and data set is different. But yeah, this is our experience so far.
Cool. So we've got a couple of questions. I'm just going to kind of summarize. Questions talking in detail about the data sets that were used to train DBRX. And I noticed that there's not really like a full kind of technical report on DBRX outlining the data in detail. Is one coming out?
So we are working on a technical report, but unfortunately, I can't tell you more than the broad categories. So I will say, if you're interested in sort of like some of the modern like specifics of data mixes that people are used to train LLMs, I would really look at the Dolma mix put out by AI2. So in particular for Olmo 1.7, here, there's a blog post that AI2 shared the full data mix that they were able to use for this model. And I think that's a great place to look for some examples of like data mixes that are really effectively able to get good scores on MMLU or on these challenging benchmarks.
Cool, thank you. So some just kind of general questions about the future of LLMs. Maybe we can make this a bit more specific. It would be good to talk a little bit about scale of the models. I guess 18 months ago, everyone was thinking like you really need to have massive models to do well on some of these benchmarks. But then Llama 3.1, I suppose, is showing that even with quite small models, you can get really amazing results in MMLU and other benchmarks that you talked about today. What do you feel like the view is changing about scale? Do you have some thoughts about the future?
Well, I think that observation that about sort of Llama 3.1 is another great example of like you can really push back the scale at which you need to go to get performance or good performance on MMLU with like increasing the quality of your data set, right? This is great, and this is sort of one of the themes that I've tried to like hammer home in this talk. Also things are changing with like people using more and more, like having access to large models like Llama 3.1 405B, right, where you can do distillation, right, and work with smaller models. I think for us, right, like I don't think our avenue is going to be like, oh, we want to, scale and, make our models bigger and bigger. What we want to do is better understand how to adapt models at a certain scale to people's domain, right? And like, I think, at least from our perspective as a research lab, is like we're really interested in taking the case where someone has their data set and finding sort of the right scale of model where we can really make improvements and make a good domain specific model for their data. Yeah, I mean, maybe the summary points there are like, yes, like data efficiency gains from data are real, and like it's really exciting, right? How we're able to get smaller and smaller models with really good performance on these benchmarks. And I think that as we start to focus more and more on like domain specific models, right, we're gonna think more and more about sort of like the models that we can use as starting points to best serve whatever a customer needs.
Great. Well, I think that's a fantastic place to end it. Brett, that was a fantastic talk. Really fascinating stuff. Really, really interesting work. Thank you so much. Thank you to the audience. Thanks to Evolution AI for sponsoring. And yeah, thanks once again to Brett, and see you all again next time.
Thanks so much for hosting, Martin. Bye.